Hey guys, this is Harold L.R. Watkins back with another video. What you are looking at is a prototype of an AI automotive cybersecurity incident and compliance assistant, a database backed a database-backed Python tool designed to organize and query cybersecurity incidences across vehicle platforms, ECU zones, connectivity paths, evidence records, and compliance controls. The problem this tool addresses is that incident data is often scattered across different systems. VIN records, Tara nodes, diagnostic logs, mitigation actions, and evidence references are not useful if they are disconnected. This project creates a structured foundation to bring that information together. The project structure goes like this. This is the project folder, starting with schema.sql, which defines the database tables, constraints. Hold on a moment. Let me bring this down so you can see it better. All right, perfect. Let's start from the top. Okay, so starting with the schema.sql, which defines the database tables, constraints, and relationships. seed.py rebuilds, look at the seed.py, which rebuilds the database and loads sample automotive cybersecurity incident data. Going to the data folder and project.db. So the data folder contains project.db, which is the live SQL or SQLite database file. This file is not meant to open like a normal text or Python file because it's a binary database file. I do not edit project.db directly. Instead, seed.py populates it. Schema.sql defines the structure, and db.py retrieves the data through SQL queries. db.py is the main focus because it separates the database logic from the interface. App.py here. So app.py is a working Streamlit dashboard preview that already imports from db.py, as you see here. Now let's go back to the schema.sql. The schema includes tables from vehicles, incidents, risks, assessments, controls, evidence, mitigation actions, and relationship mapping. The vehicles table stores VIN, make, model year, ECU zone, and connectivity type. The incidents table stores the attack vector, affected component, severity, status, and description. One important design decision is the risk score field. It is generated directly in SQL as likelihood times impact. So the database calculates risk consistently instead of relying on Python to calculate it later. Let's move to the database access layer. At the, let's go to the top of this. At the top, the database path points to data slash the data folder um, project.db. The get underscore connection function creates a reusable SQLite connection and enables foreign key support. The functions return pandas data frames, which is useful because Streamlit can display them directly. Get underscore all underscore incidents retrieves incident records with vehicle contents. Get incidents by severity uses a parameterized query with a question mark placeholder, which avoids unsafe SQL string formatting and helps reduce SQL injection risk. Get incidents with assets uses a join to connect incident with affected vehicle assets. Get incidents counts by severity, uses group by and aggregation to summarize incidents by severity and average risk score. Get open mitigation shows unresolved mitigation actions. The AI supportive function is get incident evidence for AI. It retrieves incident details, vehicle context, tower notes, link controls, evidence records, compliance gaps, and mitigation summaries. That gives a future AI model grounded database evidence to summarize the the incident or recommend next steps. Now I'm going to run the backend terminal. I'm here. First, I will run Python seed.py. So Python seed.py. This rebuilds the SQLite database from the schema and loads the sample vehicle and incident records. Then I will run the Python db.py. So Python db.py. The output shows the required database access functions working. All incidents, the parameterized severity query, the join query with vehicle assets, the group by severity summary, the open mitigation, and the AI evidence query. This confirms that Python is connecting to SQLite, executing SQLite queries and returning structured results. Before I close, I'm going to briefly launch the Streamlit dashboard. Python dash m Streamlit run app dot py. This shows that the front end is already calling reusable functions from db.py. The main focus here is the database access layer, but the dashboard confirms the backend can support a browser-based interface. This prototype now has the core layer started, a structured SQLite database, a reusable Python database access layer, and a working Streamlit database preview. This is an early stage prototype, but the architecture is real. The data model is production relevant, and the path from here to a deployable tool is clear. Thank you for watching.